Hello, this is Dr. Mears. Today we are going to be learning about mutually exclusive and independent events. This first example is going to be about mutually exclusive. I just typed up some notes so that you can have them here. I'm going to read through them first. Mutually exclusive events are events that can never occur at the same time. For example, you toss a coin and you will not be able to get a head and a tail at the same time. Events A and B are mutually exclusive if and only if the probability of A and B happening equals 0, meaning no way, no way. In a Venn diagram, the circles do not overlap. So they look like this. So these two are not overlapping. So in our toss a coin, this would be the heads and this would be the tails. So notice there's no overlap here. Okay. Let's get to the example. In the following examples, we will determine whether the events A and B are mutually exclusive. So this is what you're going to have to do for your DCCs. Number 1, the numbers 3, 4, 5, 6, 7, 8, 9, 10 are each written on identical pieces of card and placed in a bag. A card is selected at random from the bag. Let A be the event, a prime number is chosen, and B the event, B be the event, and an even number is chosen. Draw a Venn diagram. It's always good to draw a Venn diagram, even if the problem doesn't state it, because it'll help us to count out the number of desired outcomes that we have. So first, let's do that. Okay, here's our universal sets, and we need A, the prime number. So over here, what I'm going to do is I'm actually going to write out what the prime numbers are from this universal set that we have. So prime numbers are numbers that are only divisible by 1 and itself. So when we look here, 3 is only divisible by 1 and itself. 4 is not, we can divide it by 2. 5 is. 6 is not, we can divide it by 2. 7 is. 8 is not, 9 is not, and 10 is not. So we only have the three numbers, 3, 5, and 7. Okay. Next, what we're going to see here for B. So that's prime number. B is the event, and even number is chosen. So even numbers are numbers we can divide by 2. So 4, 6, 8, and 10. Okay. Before I make these circles, I'm actually going to look between these two events to see if they have anything in common, any numbers in common. So these two sets, they don't. There's no numbers that are the same in A and in B. So what these circles are going to look like is just like this, A and B. They have no overlap because there's not going to be anything that they have in common. The numbers 3, 5, and 7 are exclusive to that circle, and the numbers 4, 6, 8, and 10 are exclusive to that circle. What numbers are we leaving out? We want to make sure that we're incorporating everybody. So let's see, we have 3, 4, 5, 6, 7, 8, we're missing 9, and we have 10. So 9 is the one on the outside. So as you can see here, we have no number that is common between A and B. So let's write mutually exclusive. Because A and B is going to equal 0. So it's actually going to be an empty set. We have nothing in the set is empty. There are no numbers that they share. So let's put this in as a probability. The probability of A and B happening at the same time is 0. It would actually be, and you know what, let's do this. Let's take it a step further. Let's say there's no desired outcomes possible divided by the total number of outcomes, 1, 2, 3, 4, 5, 6, 7, 8. The total number of outcomes is 8. I like to always write that down. So 0 divided by 8 is 0. Therefore, we did verify the rule up here. This rule, that's very important. That the probability is going to be 0. We verified that it was going to be mutually exclusive because that probability is 0. So down here, I said A and B is an empty set. So the probability of A and B happening, 0 out of 8, which does equal 0. And I'm just going to extend this. No outcomes in common. just to really drive home that definition of mutually exclusive where there's no outcomes in common. Okay, let's try the next one, number 2. An unbiased six-faced die. Roll an unbiased six-faced die. Let A be the event, roll a square number, and B be the event, roll a factor of 6. So it doesn't have any information. They're not like, hey, draw a Venn diagram. We just have to prove if this is mutually exclusive or not, so we're starting from the beginning. So what I like to do is first get my total sample space. So my total sample space, we're rolling a unbiased six-faced die, so I have 1, 2, 3, 4, 5, and 6. So those are the total outcomes that I can have. That's my sample space. I'm actually going to label that as S. Sorry, I'm erasing a lot here. I'm showing you how my awesome gel pen erases. So my sample space is 1, 2, 3, 4, 5, and 6. My event a square number is a number that has been squared. So 1 times 1 is 1. That's a square number. So 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. Those are all square numbers. So let's see what square numbers I have in my sample space. So square number 1 and 4. All right, and B is the event roll a factor of 6. So a factor of 6 are two numbers that multiply to give you 6. So 1 times 6, that's a factor of 6. 2 times 3, that's a factor of 6, and I think that's it. So let's see if any of these are in our sample space. So we have 1, 2, 3, and 6 are in our sample space. Okay, so let's draw a Venn diagram because we have our sample space, we have A, and we have B. So let's draw a Venn diagram to see if they share any numbers in common. So looking between here and here, I do see that they share a number in common, and that number is 1. So automatically they do overlap, and the number that they overlap with is 1. 4 is here, 2, 3, and 6. 1, 2, 3, 4. I'm missing 5, so that's on my outside. And I have all of my numbers from my sample space, so those are my Venn diagram. So you can see here we have an outcome in common. I wrote that down. So A and B equals 1 because that is the outcome in common. So for the probability of A and B happening, we have one outcome out of a total of 6 outcomes. This needed to be 0. It is not 0, therefore, yes, mutually exclusive. There we go. Okay, that was mutually exclusive. Let's flip our paper over and let's go to independent events. Again, I start with the definition of independent event and then give you the rule. Independent events happens when the occurrence of one event does not affect in any way the occurrence of the other. Therefore, the probability of one event does not affect the probability of the other. Here's our rule. A and B are independent if and only if the probability of A and B happening equals the probability of A times the probability of B. So this is what we're going to be using to check our examples to see if they're independent. So let's do that. In the following examples, we will determine whether A and B are independent. Number 1. The numbers 2, 3, 4, 5, 6, 7, 8, and 9 are each written on identical pieces of card and placed in a bag. A card is selected at random from the bag. Let A be the event an odd number is chosen, and B be the event a square number is chosen. So first, let's just get the total number. So there's 1, 2, 3, 4, 5, 6, 7, 8. So our total in our sample is 8. Okay. Let's get our A and B written as well because we do have to make a Venn diagram. So the event A, an odd number is chosen. So in here in our sample space, the odd numbers are 3, 5, 7, and 9. In B, it's the event a square number is chosen. Again, a square number, we multiply two numbers together to get a square number. So 2 times 2 is 4 is a square number, and 3 times 3, 9 is a square number. Okay, let's draw our Venn diagram. Do these share a number? Yes, they share 9, so the circles are going to overlap and 9 is going to be in the middle. Here's A, here's B. Let's put what's left over in A, 3, 5, 7, and 9. In B, it's 4 and 9, and then let's see what we left out. We left out the number 2. We have 3, 4, 5. Oh, whoops. I'm writing all these 9s down here, and they share 9s. What am I doing here? I'm going way too fast for my liking. I wasn't supposed to do that because they shared 9. Okay. So left over from here is 4. My mistake. And right, they share the 9. Okay. So we have 2, 3, 4, 5. We're missing 6, 7. We're missing 8. And we have 9, which I want to write down all over the place. Okay. So here's our Venn diagram. So now let's determine whether A and B are independent events. So what we're going to have to do is we're going to have to use this rule, and I'm going to write it here. We have to determine the probability of A and B happening at the same time equals the probability of A times the probability of B. So let's go find those probabilities and then see if it works. So first, let's find the probability of A and B. Probability of A and B. So A and B is A and B happening at the same time. So that's 9. Now remember, we have the total numbers are 8. So there's one number that they share, one number that they can be, so 1 out of 8. And I'm going to put that into a decimal because it'll make doing our little multiplication easier. So 1 divided by 8 is 0.125. So that's the probability of both, which is going to be in the middle. Now let's find the probability of A and probability of B and multiply those together. Okay. The probability of A is going to be the probability of getting this entire circle. So if we look back up here in A, there's 1, 2, 3, 4 numbers in A. So the probability of getting A, 1, 2, 3, 4 numbers in A, is 4 out of 8. And let's find, I'm not going to get a decimal yet, probability of B. So in the probability of B, we see we have 1, 2 numbers. You can even go back here, 1, 2 numbers. So probability of B is 2 out of 8. So let's multiply our probability of A times our probability of B. So we're going to multiply 4 out of 8 times 2 out of 8. And we're going to see what we get. Now, on the calculator, if you do not want to work with any decimals, if you just want to put this in your calculator, you simply really can do parentheses 4 division sign 8 and parentheses and 2 division sign 8. You can just really put it in your calculator like you see it. You don't have to worry about transferring anything over because what this will give you is the actual decimal. And that's why I went and I changed that to a decimal. So you now can see this 0.125 really does equal those two probabilities. So this is going to be independent. So this is 0.125 here. So we can say, yes, independent, 0.125 equals 0.125. There we go. And so showing all of this work, especially I wrote down what the rule is here. I showed my work for the probability of A and B. I also showed my work for the probability of A times the probability of B. And I showed that those two were equal, so I can say yes, independent. All of this work needs to be shown to determine whether they're independent events or not. All right, let's take a look at our last example. And so our last example, we're not looking at the actual numbers inside. They gave us the totals already. So they gave us for C, just C, it's 12. Both is 8, just P is 2, and on the outside, none is 18. So let's see what this question is about. The Venn diagram shows the number of students who take chemistry and or physics in class. Determine whether taking chemistry and taking physics are independent. So the C stands for chemistry and the P stands for physics. What I like to do here is I like to get a total count. So if we look at the C circle here, the 12 and the 8, when we add those together, we're going to get the total number of people who take chemistry, and that's 20. And I got that by adding 12 and 8. The total number of people who take physics, so this whole circle, we're going to add again 8 and 2. So the total number who take physics is going to be 8 plus 2, which is going to give you 10. And now I want the total number of people in the class. So what I'm going to do is add up my 12, my 8, my 2, and my 18 for people who take neither. And what I'm going to get is 40. I need those numbers to determine my probabilities. So it's important to have all those totals. So that's what I always do first. Okay, now let's write the rule down. Probability of A and the probability of B has to equal the probability of A times the probability of B. Now let's go search for those probabilities. First, the probability of A and B happening at the same time. Okay, Now remember, we're looking for our total number, which is 40 students. How many students take both? That's 8. This is the A and B. This is the both. So there's going to be 8 out of 40. I'm going to reduce that to 0.20 divided out because that will help me later. All right, let's find the probability. Oh, this is not A and B any longer. What is this now going to be? Let's change it. This is going to be C and P. So my A and B are now C and P. So we're just using the same rule, but instead of saying A and B, I just substituted what the letters were that we're using for this. Okay. So let's find the probability of chemistry. So the probability of chemistry, remember we have 40 total students. This is where this total comes in handy. This is going to be 20. Okay. Probability of the students taking physics, again, out of 40, and we're going to look how many take physics altogether, and that's 10. So now let's use our rule here, and let's find, does the probability of students taking chemistry and physics equal the probability of students taking chemistry times the probability of students taking physics? Well, this is 0.20. Does that equal 20 over 40 times 10 over 40? Again, you can simply do that on the calculator right as is, and what you're actually going to get is 0.125. And so these two numbers here have to be equal, and right now they are not equal. Since they are not equal, we're going to write not independent. And so this work now proves that the events chemistry and taking physics are independent. This proves it, and we prove that they're not independent because these two quantities are not equal. This has been mutually exclusive and independent events. Thank you for listening. Hopefully it helped.